Welcome back to Algorithms and Uncertainty. Today we will be talking about a problem which apparently doesn't have any uncertainty inside it, and it really does not have, namely the maximum flow problem. I hope all of you are familiar with this problem. So we are given a graph with edge capacities and we have to find a maximum flow from a source to a sink node. And what will we do? We will design an algorithm for this problem, which will make use of our experts algorithms, which we've seen in the last lectures. And why are we doing this? Well, on the one hand, it is, I think, a surprising application of these experts algorithms. But on the other hand, you'll also see a template of how to design fast algorithms for the maximum flow problem, which are actually used in very modern flow algorithms. So the modern flow algorithms are not too much different from what we'll be seeing today, although they are much more sophisticated. So let's first recap the maximum flow problem. In the maximum flow problem, we are given a graph with edge capacities which we'll call CE, a source node which we call S, and a sink node which we'll call T. And what is our task? Well, let script P denote all paths from S to T. And we now have to assign flow values xp to all the paths in P such that, well, on the one hand, these have to be non-negative. Then we also need that the flow on a certain edge is no more than the capacity of this edge. And this has to be true for all edges. And we want to maximize the flow overall, so the sum of the xp. So we're using a slightly different formulation from what you typically see in an undergrad algorithms class, because we are assigning flow values to the paths rather than to the edges. So usually you will say, okay, I want to assign a flow value to each edge, and then I'll have to make sure that flow conservation is fulfilled. Now here we're choosing this slightly different way, which is equivalent and easier for us to work with today. Namely, we'll assign a flow value to each path such that, well, on each path we have a non-negative flow value and the capacities are not exceeded. And how do we say this? Well, we have now that the flow, summing up the flows on all paths that include a certain edge E, all these flow values together, they may not exceed this CE, the capacity of edge E. And our goal is now simply to maximize the sum of all flows of all flow values along all paths, which means nothing but how much is leaving the source or how much is entering the sink. This has the advantage, which we'll not make use of today, but it has the advantage that it also easily generalizes to multi-commodity flows where you have multiple sources and multiple sinks. And as a matter of fact, everything that we're doing today, you could in principle also easily extend to multi-commodity flows, but I'm just not doing this because it will make things just more complicated than it has to be. Good, so we want to solve this problem. Apparently it has nothing to do so far with experts' problems with uncertainty whatsoever. But how will the experts algorithm be helpful? Well, what we'll be trying to do is we'll be trying to increase the flow always one path at a time. So this is exactly what you also know from this Edmonds Karp algorithm, for example, where you're always choosing the shortest path in the residual network from the source to the sink, as long as there is such a path, and when there's no further path, then you have found your maximum flow. Well, this is not exactly what we're doing today, but it is in a way similar and also in a way different. There will be no such thing as a residual network. What we'll do instead is we'll assign lengths to all edges in this flow network. And then we'll repeatedly find the shortest path with respect to these edge lengths. And along this shortest path, we will then augment our flow. We'll send some flow along this path. Namely, we'll just route as much flow as possible along this path. And where do these edge weights come from? They are coming exactly from an expert's algorithm. So in every time step, so we'll have multiple time steps, and in every time step, our expert's algorithm proposes some edge weights. And based on these edge weights, we will then find the shortest path. And then whatever path we've chosen will define whatever feedback we'll give back to the expert's algorithm. And then the expert's algorithm, based on the feedback that it got, will choose new edge weights and new edge lengths, which then we again use to find the shortest path and send as much flow as possible along this particular path. This is the general structure, somewhat similar to these flow algorithms that you know probably, where you send flow along certain paths. So that is still the same. In every time step, in every iteration, we will increase the flow along just one fixed path. But instead of having this residual network thing, we have these edge lengths which are determined by an expert's algorithm. So let's first recap what we know about experts' algorithms. Well, not everything. We don't have to recap everything that we know about experts' algorithms, but there are just only a few things that we'll have to remember for today so that then we can define our algorithm. Let's recap some of the definitions for online no-regret learning that we'll be using today. As a matter of fact, I'm slightly changing notation today because otherwise we'd have notation conflicts with all the notation that is arising in the maximum flow problem. For example, we'll have M experts rather than N experts that we had before, because our experts will correspond to the edges and not the vertices in the graph, and usually you write M for the number of edges in your graph. So what do we have? We have these M actions which are also called experts in this setting. And then there are these gain vectors. Before we always had these cost vectors, now these could be reward or gain vectors, G1 through GT. So this is the superscript is the time step, and GIT, this is the gain of action I in step T, and GIT is somewhere between 0 and 1. And now in step T the following happens. So we'll have these capital T steps. The algorithm chooses a probability vector. So far we always called this probability vector P. Let's call it Y today to not get confused with paths. Paths will be called P today, and we'll call the probability vector Y today. And then the algorithm has a gain of the expected gain that you're getting when you're drawing one action according to this probability vector. And then the algorithm gets to know all of GT. And then the algorithm again chooses a new probability vector YT plus 1, gets the respective gain, and then it gets to know the vector GT. And then we defined the regret of an algorithm. As the maximum gain minus the gain of our algorithm. So this Gmax, this is the best single action in the sequence. And GL, this is just with a capital G, this is the sum of all algorithms gains overall time steps. So we might also write it as the sum of the y's times these small g's. So what is different here is that we have the gains rather than the costs, but we already talked about this, that you can interpret or you can just turn everything around, and then what we're interested in is how is the best action, so what action gets the maximum gain versus what gain does our algorithm get. And now it's of course, the regret will still be non-negative, so we're saying what is the maximum gain that you can get minus what gain are you getting. And for this we can, for example, apply the multiplicative weights algorithm. And the multiplicative weights algorithm will guarantee us that the gain it is getting in t time steps, forgot the superscript capital T here, the gain in these capital T time steps is at least 1 minus eta times the gain of the best action minus ln m over eta. Recall that today m is the number of actions or number of experts and not n. So this looks a tiny bit different than the bounds that we had before, because there we had that the cost of our algorithm was at most 1 plus eta times the cost of the best action, or best expert plus this thing. But other than that, other than actually every sign here is turned around, everything still is the same. So we can also see that the regret is at most eta times G max plus ln m over eta. Good. So these kinds of algorithms, or in particular we'll use multiplicative weights today, but we could in principle use any no-regret algorithm, because all that we will be relying on is that this regret vanishes, or no, this regret divided by capital T goes to 0 as capital T increases. That's maybe not as explicit here. This of course depends on the choice of eta. We'll see both. We'll see on the one hand the guarantee if you plug in any no-regret algorithm, and then we'll also plug in this precise guarantee to then see what running time for a flow algorithm we're getting if we're using this particular multiplicative weights algorithm. Good. So how does now our algorithm work? It somehow, our flow algorithm that we will be designing, somehow interacts with this experts algorithm. So this experts algorithm actually has some actions available to it, and then decides on a probability vector y. And how does this relate to the flow problem? Well, but this probability vector that the experts algorithm is choosing here, we will actually interpret as a choice of edge lengths. And based on these edge lengths, then our flow algorithm will try to augment the flow. And then, based on how clever this experts algorithm choice was, we are more or less successful, and we'll give some appropriate feedback back to this experts algorithm, so that then in the next time step it will again propose some edge weights or edge lengths that we will again use to then again augment our flow. But before getting there, let's first talk about flows and edge lengths. Because based on LP duality, we can now also write down a lemma which helps us stating that for a flow to exist, it is necessary that there exist short paths for whatever edge lengths can be chosen. In order to define our algorithm, we will have to use edge lengths. And then our algorithm will choose shortest paths according to some edge lengths. But how do maximum flow problems and edge lengths, how do they correspond to each other? What do edge lengths have to do inside this maximum flow problem at all? Because there is no such thing as an edge length in the definition of the flow problem. Well, let's see this. Let's first see how you could write down the flow problem as an LP. In order to define our algorithm, we will have to use edge lengths. And then our algorithm will choose shortest paths according to some edge lengths. But how do maximum flow problems and edge lengths, how do they correspond to each other? What do edge lengths have to do inside this maximum flow problem at all? Because there is no such thing as an edge length in the definition of the flow problem. Well, let's see this. Let's first see how you could write down the flow problem as an LP. You would want to maximize the sum of flows along all paths subject to the capacity constraints, meaning that on every path, on every edge, the capacity is not exceeded. And of course, you would also want to have that there's only non-negative flow values on every path. Now let's see what its dual LP will look like. Well, it's now the following problem. We now have a variable for each constraint that we had before. So before we had a constraint for each edge, which means now we have a variable for each edge. And I'm calling these ZE now. And what are the dual constraints? We'll have a dual constraint for each variable in the primal. So what we'll need is the following. We'll need that the sum of the ZE is at least 1 for all the edges on a path. The sum of the dual variables on a path always has to be at least 1. And all of these ZE are non-negative. So these are the edge lengths that I was talking about. Namely, in the dual LP, we suddenly have edge lengths. These ZE you can interpret as lengths of the edges because they're all non-negative. And now a choice of edge lengths would be feasible if for every path from the source to the sink, the edge weights are sum up to at least 1. So the path length from the source to the sink has always to be at least 1. And what is now weak duality telling us? For every feasible choice of such edge lengths, this objective function value will always be at least as much as the optimal flow value, so the maximum flow value, because whatever we're getting down here will be at least as much as what we're getting up here. Okay, interesting. But we'll actually rephrase this a tiny bit, and that's why also we will prove this from scratch, because to get the precise result that we'll need, we'll now actually keep this thing here fixed. This C times ZE, we'll choose somebody chooses edge lengths where this thing here is fixed, and then we claim, okay, they're always, if this here is, for example, exactly the maximum flow value, then there has to be a short path. So even if you didn't follow these thoughts regarding duality, doesn't actually matter, because we can now just write down a very simple lemma regarding any choice of edge lengths versus the maximum flow value. Namely, we can show that if there is a flow of value f star, then for all choices of edge lengths, ZE, that sum up or such that capacity times edge length sums up to f star, there is a path P such that its length is no more than 1. Good. So if you are familiar with duality, you'll see, okay, this lemma is stating nothing but that this LP gives us a lower bound on the objective function value, but it's slightly different here because we're keeping this Z fixed to such that the objective function value should be f star, and then we're talking about the constraints. So maybe let's not bother about any more about duality, and let's just see how we can show this lemma here. How would we prove this? Well, we're now saying if there is a flow of value f star, so let x be a flow of value f star. As it is a feasible LP solution, what do we have? We have that on every edge, the sum of the edge of the flows along the paths that that include this edge, this is no more than the capacity of the edge. Or we might as well write the following. If we choose to divide by the edge capacity, then the sum of the xp divided by c is no more than 1. And what does this imply? This now implies the following. Take the sum over all edges and then the c times z, and now multiply this with what we have here, with this thing. Then, how big will this be? Well, we know that this here is exactly f star. This here for every e is no more than 1. So we have that this is at most f star. Good. But what we can now do is we can reorder this sum. Because what we have here, we could also write as follows. we could also instead take the sum over all paths and then take the xp and then take the sum over all edges on this path and take the ze value. Then, because every edge is appearing on every path here, so we're summing up over all edges and then over all paths which contain this edge. Now we're first summing over all paths and then we're summing up over all edges that are contained in this path. Now what would happen if all of these were bigger than 1? Because recall that we wanted to show that there is a path of length at most 1. So if we suppose that the sum of the edge lengths is bigger than 1 for all paths, then what do we have? Then we have that the flow that we have here has to be strictly smaller than f star, which is a contradiction to this x being a flow of a value f star. Good. So the idea here is no real magic. It is just reordering the sum. And then you see, okay, whatever edge lengths you choose, whenever you fulfill the constraints, that the sum of the capacity times the edge length is f star, then there has to be a path of length at most 1. Regardless of how you choose these edge lengths. Now let's go one step further and let's divide, or let's change the variables here. Change the variables from ze to ye. And how is ye defined? Ye will be exactly ce times ze divided by f star. Namely, what we get is the following corollary. If there is a flow of value f star, then for all choices of ye with sum of the ye being exactly equal to 1, there is a path P such that the sum of the ye divided by ce is at most 1 over f star. Good. So this corollary is actually not really surprising when you see this lemma, because all we're doing is we're replacing this ZE by YE divided by CE times F star. Good. But how does this corollary help us? Well, it's no coincidence that now here I'm calling this YE, and before, when I was talking about the expert's algorithm, I was calling the probability distribution YE, the probability vector, because here now what is happening is that these YE sum up to exactly 1. So, the way we can interpret this now is that, or how does this help us towards designing the algorithm? It tells us that, well, there will be the expert's algorithm, which will propose these YE, which are nothing but, which we could also interpret as a probability distribution over the edges, or which we can interpret like this as a choice of edge lengths, as a choice of these ZE. And then the expert's algorithm is trying to show us, well, there cannot be a flow of value F star, because see, these are the Y's that I'm choosing, these are edge weights that I'm choosing. But then we say, oh no, that's not true. Because what we then do is we find a path along which we then can augment the flow, and we'll do this based on the YE. And we'll then see, okay, because, well, conditional on the fact that there is a flow of value F star, all we now have to do is we'll have to choose the, well, one path for which we know that it exists, where the sum of the YE divided by CE is at most 1 over F star. And how would we find such a path if we know that such a path exists? Well, this is nothing but the shortest path problem. Finding such a path is easy when you know the YE and the CE are just fixed, so all you have to do is you'll have to find the shortest path. And this is what will now be happening in our algorithm, is that we'll have our expert's algorithm proposing the YE, and we then choosing a shortest path with respect to these YE, and then augmenting the flow along the respective path, and then telling the algorithm, the expert's algorithm, okay, this is where you got your gain, because, or this is how you made us pay a lot for the length of this path. I've now tried to give you some intuition on why our algorithm works, how our algorithm works, but maybe let's now go into the details of how we define the algorithm. Namely, it works as follows. We'll have capital T time steps, 1 through capital T, and how does such a time step, such an iteration of our algorithm work? We will get a probability distribution YT from the expert's algorithm. And then we will compute capital PT as the shortest path with edge lengths YET divided by CE. And then we let CT be the minimum of all capacities on this path. Then we are augmenting our path, our flow, namely we'll send a flow of CT along path P, the path PT, and no flow along any other path. And then we return GT to the expert's algorithm, where the gain that the expert's algorithm has associated to edge E is CT divided by CE if the edge is on the selected path and 0 otherwise. So this is what is happening in the capital T iterations. We're doing this capital T times. So I hope you see that we now have the expert's algorithm. I should have mentioned, and maybe let me say this once explicitly, because I maybe said this too implicitly so far. We'll have one expert for each edge. And now this expert's algorithm proposes this vector yt. Then we compute the shortest path, because this yt we can understand as edge lengths. We'll compute the shortest path with respect to these edge lengths. And then we'll see, okay, how much flow can we send along this path? And then we'll tell the expert's algorithm, okay, your gain is this much for the paths, for the edges on the path, and it is 0 otherwise. So how big is this? Well, suppose now all edges had a capacity of 1. Then the expert's algorithm would get gain from every edge which we chose. And now, of course, it matters how much probability mass did the expert's algorithm put on this particular edge, or how long did the expert's algorithm make this edge. And the goal of this expert's algorithm is kind of to make the edges very long that we are choosing, because this is what the expert's algorithm is getting gain from. Now, this is what we're doing in every of our iterations. Now, how do we get to our final flow? Well, what we'll do eventually after our capital T iterations is we'll compute x bar, which is the sum of all these xt's. This here, this is xt, this is the flow increase that we're choosing in step T. X bar, this is the overall flow. Well, maybe this x bar will actually not be feasible, but as it turns out, we can make this feasible. What we'll also do is we'll compute the maximum gain, so taking the maximum over all edges, what is the gain? of this edge, and then what we'll do is we'll return as our flow 1 over the maximum gain times x bar. Good, so this is the idea of our algorithm. And the first thing that we should probably talk about is, why should this be feasible? Why should we be getting a feasible flow out of this? Well, of course, in every step we're augmenting our flow somehow, and then we have this x bar. But this x bar certainly is not feasible, because all that we're doing here in a certain step, that is just sending flow along a certain path. So each of these xt individually, that is of course feasible, because this is exactly what we're doing here. We're choosing one path pt, then we're sending as much flow as possible along this path. But this would only be feasible if there were no other flows involved, if there was no flow along any other path. So this is why this won't succeed immediately. And what we'll then be doing is we'll divide this by the maximum gain. Why should that be true? Why should this work out? Well, let's see. We'll now first show that this computes actually a feasible flow. So the algorithm computes a feasible flow x. Why is that true? What do we have for every edge E? How big is the gain that we're associating to this edge? Well, this was the definition of the gain. So the sum of these gains is nothing but take the sum over all time steps or iterations in which we were choosing this in this edge in our path, and then we'll have the capacity that we chose in this iteration divided by the capacity of this particular edge. This capacity of this particular edge is the same always. So we'll have nothing but the sum of all time steps in which this edge was chosen on the, with the respective path, and then how much flow did we want to send along the path in step t. Now, how can we rewrite this here? This CT, if you recall, this is exactly the flow that we're sending along the path PT. So, what is it that we're summing up here? Well, we might as well write this as take the sum over all iterations, not only the ones where we're including edge E in the path, and then take the sum over all paths, but only the ones including edge E. And then take the xpt variable. Why does this work? Well, actually, this xpt is 0 unless p is exactly pt. So, and then it is ct. So by just the definition of xpt, this is exactly the same thing. Now, what does this tell us? This tells us that this sum here is nothing but and take the sum over all paths, which include edge E, and then take the sum over all time steps or iterations, and then sum up the xpt. But this thing here, this we exactly called x bar p, because x bar, this was just summing up all the xt vectors. Good. So this is the gain of one particular edge overall. And what does this mean for the maximum gain of any edge? The maximum gain of any edge, this is nothing but take the maximum over all edges of this quantity. And what does this tell us? This tells us that if we now divide xp bar by g max, then, and what does this tell us? Well, we are dividing by g max. So this tells us that the sum of the paths which include xp, e in xp, well, this is exactly what we defined as 1 over g max times the xp bar. And given this, we see, okay, this will be at most CE, and this holds for every edge E, which means nothing but that our flow that we're computing actually fulfills the capacity constraint. Good. So we have an algorithm which actually computes a feasible flow. And this is, I think it takes some time to accept that these calculations are this simple and still everything works out. So I think what makes all of this difficult is rather the conceptual part than following these calculations here, which see, okay, this is actually correct. We actually fulfill our capacity constraints by computing a flow like this. What, of course, we don't know yet is whether this is a good flow or not. And this is what's coming next. Namely, we want to show that this computes an approximately maximal flow. And the approximation guarantee depends on how many iterations we are running here. Now we want to show that we're actually computing an approximately maximal flow. And how can we do this? What will be the idea to show this? Well, we have our lemma showing that whatever values of ye might be chosen, if there is a flow of value f star, there has to be a short path from the source to the sink. But on the other hand, we'll also use, well, first of all, this tells us that the choice of the path length or the overall path is short that our algorithm is using because it's computing the shortest path. But then on the other hand, we will be using the regret property of our algorithm, of our expert's algorithm, and that we have a regret bound for this expert's algorithm. So in particular, what this expert's algorithm might be doing would be to just set a ye of 1, so what the algorithm is comparing to itself is if it put a ye of 1 for any possible edge in the graph. So what we'll be showing is the following. We will show that the flow x computed by our algorithm has value at least f star times 1 minus the regret of the no regret algorithm divided by G max, by the maximum gain, where f star is the value of an optimal flow. How do we prove this? Well, let's first talk about our experts algorithm. In a fixed time step t, what's its gain? Its gain is nothing but take the sum over all edges, this yet times get. Yet is something like the probability that it chooses this edge. But how big is this get? This get, I hope you remember, this was the following. It was for every edge on the path that is chosen by our algorithm, it was ct divided by ce, and for every other edge, it was simply 0. So this is why we can rewrite the gain of our experts algorithm in a certain time step like this. Cool. And what we see is that this CT that doesn't depend on this particular edge, that's just fixed for this particular time step. Now, what do we know about this? Where was this coming from? This is for all paths, or for the particular path that we are choosing in time step t, in iteration t, it's the yet divided by ce. And maybe let's go back to our algorithm to see which path did we choose. We chose to compute a path pt as the shortest path with respect to exactly these edge lengths. And what else do we remember? We remember that we had this corollary. If there is a flow of value f star, then for all choices of these ye, which sum up to 1, there is a path such that its length of these with respect to the ye divided by c is at most 1 over f star. And now here in our algorithm, we are computing the shortest path with respect to these edge lengths. And we know, of course, that there is a flow of value f star, which means that because this is a one choice of these ye according to our lemma, that the length of this path will be at most 1 over f star. This is by this corollary. So we're getting that the gain of our experts algorithm in time step t is no more than ct divided by f star. Okay, this is the one thing that we have regarding the gain of our experts algorithm. We can then say what's the overall gain of our expert's algorithm. The overall gain of our expert's algorithm summing is nothing but summing this up over all time steps. So this is at most 1 over f star times the sum of these CT. But how big is the sum of the CT? CT, this was, maybe let me once again go back to our algorithm. CT, well, this was by how much we're increasing the flow with our xt. And the x bar that we're computing eventually, this has flow inside it of the sum of all the CT. So this thing here is nothing but how much flow we have inside this, well, not actually feasible flow x bar, because this was how much we were trying throughout the algorithm to send from the source to the sink. Good. So this is this. And how did this relate to our flow that we're computing? Well, this was exactly G max times the flow that we are computing. Because we divided the flow, or the non-feasible flow x bar, by G max to get the flow that we are returning. So this is already relating the flow that we're returning to the gain of our algorithm. But the gain of our algorithm, this can also be related to the best possible gain. So if we now start this from the other side, we have that the gain of our algorithm is, of course, at least, or we could even say in this case equal to the maximum gain that is possible minus the regret. This is just the definition of the regret. And now let's put this together. We'll see that the sum of the flows along our paths, this is at least f star over G max times G max minus the regret. Which is nothing but f star times 1 minus the regret divided by G max. And, believe it or not, this was exactly what we were claiming. Good. So here actually everything accumulates. On the one hand, we have our corollary, which was telling us that these paths that we are computing, they have to be short, just because there are kind of no good edge lengths that make it difficult for us. Good. This gives us a lower bound and the gain of our expert's algorithm. But then on the other hand, this is exactly what we're doing here. The gain of our expert's algorithm is somehow the best possible gain times the flow that we're computing divided by the optimal flow. And then we have the other side that, well, our algorithm is probably a good algorithm. So far we haven't actually used that. The regret is small. This is still hidden inside here. So even if the regret is big, for example, if the regret is G max, then this ratio will simply be 0. But what this is telling us is that, well, if the regret is small, then hopefully we are now computing something which is good, because this gain here of our algorithm will be close to the best possible gain, which means that our flow and the best possible flow have to be close to each other. Now there's one more thing to turn this into a good bound, namely how big is this G max? Because if this G max were something like 0, then no regret bound at all would help us here. But we can now derive a lower bound on G max. Namely, we can show that the G max that we are getting is at least T over M. And why is this? Where were these gains coming from? The gains were coming from this here. The gain of edge E in step T was the capacity of the smallest capacity on the path PT divided by CE for an edge contained in this path. But what you'll see is there is, of course, on this path, there is an edge for which the capacity CE is exactly equal to CT, which means that in every step there is one edge for which this ratio is exactly 1 on the path. And this now lets us do the following. In every time step t, there is an edge such that its capacity is exactly to the CT. So the gain of this edge will be 1. So how big is the maximum gain? Well, what we're doing here is nothing but taking the maximum over all edges, taking the sum over all time steps, and what we could do instead is take the average of all edges. And here in this sum, we know that in this double sum, we know that for each t, there is at least one GE which is bigger than 1. So what we could do is we could reorder this sum. And now this thing here will be at least 1. So overall this will be at least capital T divided by M. Good. And now this takes us further, because if we now plug this in to our guarantee, then we'll see, okay, the flow that we're computing has value at least f star times 1 minus regret times m divided by t. And if you now have a no regret algorithm, then this regret grows sublinearly in t. So like square root t or so. And then, what does this mean? This means that this thing here will always tend to 0 if you just make t large enough. So you can compute a 1 minus epsilon approximation of your optimal flow for every epsilon that you like. Namely, just make the t large enough. If you only make the t large enough, regardless of what no regret algorithm you're using, you will always get such a, for every no regret algorithm, to be very precise now, for every no regret algorithm, you can find a capital T such that if you run this no regret algorithm for capital T rounds, then you'll have a 1 minus epsilon approximation of the optimal flow. Whew, good. But I want to now make this a little more precise, namely in the context of multiplicative weights. For multiplicative weights, we know our regret guarantee. It was square root t times log number of experts. So what is it that we're getting here? So for multiplicative weights, we have that the regret after t steps is at most eta times g max t plus ln m over eta. And so, what was it that we had before? We had that the value of our flow is at least f star times, 1 minus the regret by time t divided by g max t. And how big will this be? This will be at least 1 minus f star times 1 minus eta. And now the g max term cancels once, minus ln m over eta times g max t. And now we can say, because this g max is at least t over m, that this is at least f star times 1 minus eta minus m divided by t times ln m over eta. Good. So what we could do is we could choose eta to be epsilon over 2 and t being equal to 4 over epsilon squared times m times ln m. Then what we're getting here is that this here, how big is this? This will be epsilon over 2, so we'll get that this is f star times 1 minus epsilon over 2 minus and then see what you're getting here. T times eta, how big is this? This is epsilon over 2 over epsilon times m times ln n. And if you now do the math, you'll see, okay, this is also epsilon over 2. So this is nothing but f star times 1 minus epsilon. Cool. So if we use multiplicative weights, then the algorithm computes a 1 minus epsilon approximate flow using 4 over epsilon squared times m times ln m shortest paths computations. Its overall running time is O of 1 over epsilon squared times m squared times ln m. How am I getting there? Well, just plug in the running time for one shortest path calculation, and then you'll see, okay, this is effectively m, so we'll have to multiply this by another m. Good. So this is what we can get out of this. We have now a 1 minus epsilon approximate flow algorithm with running time 1 over epsilon squared times m squared times ln m. And how did we get there? Well, this running time is mainly determined by how often we'll have to compute a maximum flow, because this is what dominates the running time of one iteration, of one of our capital T iterations. And how many iterations do we have? Why did we choose the number of iterations like this? Well, just because the guarantee that we got was of this form, and here we then chose eta, so that this became epsilon over 2, and then we chose t, so that this also became epsilon over 2. And where did this guarantee come from? Well, let's zoom out a bit. As much as I can here. This guarantee was coming from originally this lemma, which showed us a lower bound for the value of our flow that we're computing here, where we were using this corollary, and the fact that we were computing a shortest path. This is how we got this relation to the optimal flow. And then we also had to use this very simple lemma to show that the maximum gain of every is big enough so that choosing t large enough, actually this term here becomes small. Good. So what you see is it's actually not super complicated. Once you have this algorithm for the experts problem, or once you've analyzed the multiplicative weights algorithm, you can also reuse this for certain settings. In particular for this setting, you can use this algorithm to, yes, what does it actually do here? It proposes some sort of edge weights. And or edge lengths. And the key was this earlier lemma that we had, which was this one here. This was the actual lemma that we had originally. This is now written in terms of these edge lengths ZE. And there we said, okay, if there is a flow of value f star, then this and that. Now what our algorithm actually shows is the same thing, but the other way around, namely that this is also an if and only if, because what we were able to do is that whenever there exists these edge lengths, or whenever for all choices of these edge lengths we have this property, then we are able to compute such a path. So in some sense, this is an if and only if, and well, this is the elephant in the room here, is this is strong duality. By strong LP duality, because the optimal solution to this and to this are the same, this lemma here is effectively an if and only if. And interestingly enough, to some extent, our algorithm gives a constructive proof that this lemma is also an if and only if. Good. And next time we'll see that this goes even further. That using this multiplicative weights, you can actually see that a property like this, using the multiplicative weights, we can show that a theorem called the minimax theorem holds, which is actually a very abstract theorem about two players in a zero-sum game. But what we'll then also see is that the game that we are kind of playing here, our algorithm choosing paths in this flow network versus the expert's algorithm choosing these edge weights, this can be interpreted as such a zero-sum game. And this is what we'll see more generally in the next lecture, that there we can always use this multiplicative weights algorithm as, or generally any no-regret algorithm, to devise such a strategy for an antagonist for us. But this is all what we're doing next time. I hope you are as excited as I am about this unusual application of an algorithm which we originally defined for a setting of uncertainty. Now there's no uncertainty here at all, except for that in advance we don't know the flow value, afterwards we do. Of course, things are a little complicated, although the math itself, I think, is pretty easy and clean. If you do have any questions, please reach out to me, and otherwise see you next time. Stay safe. Bye.